Our question in this video is, how do we solve equilibrium problems? To understand how to solve equilibrium problems, we must first understand what equilibrium is. So looking here, equilibrium is what it sounds like, to be equal. All of the forces equal each other out, and therefore they cancel. So when all of the forces cancel, we say that we are in equilibrium. That means that the forces that are up are going to balance out the forces that are down, and the forces that are left are going to balance out the forces that are right. Now you can't actually see a force, so how do you know if something is in equilibrium? How do you know if the forces are balancing each other out? And the way to see visually if the forces are balancing out is that there is no acceleration. That means that the object is either staying at rest or it is moving with a constant velocity. Either way, if it is at rest or if it's moving at a constant velocity, we're going to be in equilibrium. Now, once we know we're in equilibrium, how do we proceed there? Well, tips for solving any kind of force problem is we always start with a free body diagram. Then, as before, we always write down what we know, what we are given in the problem, and what we are looking for, what we need to find. Now, when going to the equations, if you're in equilibrium, meaning you're at constant velocity or not moving, which is still a form of constant velocity, then all the forces in the x direction cancel out. They all add up to 0. And all the forces in the y direction cancel out. They all add up to 0 as well. If you're not in equilibrium, this is what we'll get to later on, then we use the second law of motion in that all the forces equal to mass times acceleration. But in our problems for this year, they will still cancel out in at least one of the directions. That's not always the case, but at least it is for this year for us. Let's go through one example together. This is force problem number 6, equilibrium, the first in that series. It says a museum curator moves a 145 kilogram aluminum sculpture across a horizontal steel platform. It takes a force of 870 newtons to move the sculpture at a constant velocity. So that is our clue that we are in equilibrium, constant velocity. We want to know what is the coefficient of kinetic friction between the aluminum and the steel. First thing we always do is we draw a free body diagram. So here's our sculpture. And we always have gravitational force present. So no matter what, we'll always draw in the gravitational force. Now the next thing we want to see is there a surface? And yes, there is a surface. And if there's a surface, there's a normal force which is perpendicular to the surface. In this case, the normal force is up. Then we want to see if there is friction. Well, it's moving, and so there is going to be friction. I'm going to say that we are pushing the sculpture to the right. And therefore, the friction opposes the motion. The friction would be to the left. Now, in this case, since it is moving, it is kinetic friction. If it were not moving, it would be static friction. Then we see, is there a rope, string, or cable? The answer is no. So there is no tension force. But there is an applied force, the force that we apply to it to move it. We are applying the force to the right. So now we have our free body diagram. We write down our givens. The first given that we have is the mass. And the mass was given to us as 145 kilograms. Then we are also given this 870 newtons. That is our applied force. We want to find what is the coefficient. So we are looking for the coefficient, which is mu, and it's kinetic friction, so it is subscript k. Now there's one thing that we always know that we're going to use later on, and that is the gravitational field strength, which is 9.81 newtons for every kilogram. So now let's start to solve. We are in equilibrium. And what that means is that our upward forces equal our downward forces. So one of the equations we're going to write is that the normal force is equal to the gravitational force. We don't know the gravitational force, but we do know the mass. We're going to have to do a side calculation here and solve for the gravitational force, which is m times g. Our mass is 145 kilograms. G is 9.81 newtons for every kilogram. And we get that the gravitational force comes out to be 1,422 newtons. So therefore, that is also the normal force. Now the other thing that we have is that the force to the right is equal to the force to the left. Again, in equilibrium, they simply equal each other. So we have that the frictional force, kinetic friction, is equal to the applied force. So again, our up equals the down, and our left equals the right. Now we know the applied force is 870, so therefore the friction is also 870 newtons. Now this has nothing to do yet with solving what we need to find, which is the coefficient. But if you look for your only equation with the coefficient of friction, there's only one equation that we have so far with the coefficient of friction, and it looks like this. And so what we've done was we solved for the normal force, right here, and we solved for the friction force, which is here, and now we're going to solve for that coefficient. So 870 newtons is equal to our unknown coefficient times our normal force, which is 1,422. We divide each side by 1,422, and we get that our coefficient is 0.61. There are no units for the coefficient. The coefficient is simply describing how rough or smooth the surface is. So the larger the number, the rougher the surface. The smaller the number, the smoother the surface is.